In this session 5.4, we will cover tensile strength tests and point load test. The tensile test we use commonly for load testing is the Brazil test. We will go through the Brazil test now in part A. As this test is one of the common tests for rock materials, the International Society for Rock Mechanics has produced the ISM suggested method in 1978. In this document, there are a few test methods being covered. However, in our session here, we will focus on the Brazil method, which is part 2 of the ISM 1978 suggested method. The suggested method for determining indirect tensile strength by the Brazil test. You may be wondering why rock mechanics people determine rock tensile strength using the Brazil method, but not the other methods such as direct tension or bending. It is mainly due to the accessibility and the preparation of test specimen of rock material. It is rather difficult to prepare dog bone specimen from rocks. On the other hand, the most common sources of rock samples are rock cores, and it is very easy to cut the core into circular discs, which is the shape required for Brazil test. By comparison, it has been proven that the tensile strength obtained from the Brazil test is basically the same as that from the direct tensile test. The test apparatus needed for the Brazil tensile test is fairly simple. You will need a loading machine or device to apply and measure axial load. The central piece of the apparatus is the Brazil test assembly for loading the specimen, shown by the figure on the right. It consists of the upper and the lower jaws to catch the specimen, and the half ball bearing to ensure loading is axial. The assembly are made of hardened steel. You also need a micrometer die gauge with accuracy of 2.5 micrometer to measure the movement of the moving jaw. We mentioned earlier that the test specimen is a circular disc, commonly cut from rock cores. Specimens are circular discs with a thickness to diameter ratio of 0.2 to 0.75. The diameter should be approximately 50 mm, and the thickness therefore should be between 10 and 35 millimeter. The cylindrical surface should be free from obvious calling tool marks. The cylindrical surface should be smooth. Any irregularities across the thickness should not exceed 0.025 mm. The two-end face should be flat to within 0.25 millimeter and parallel to within 0.25 degree. To perform the test, we should have the specimen wrapped around its periphery with one layer of the masking tape. Then we place the specimen between and in the center of jaws of the Brazil assembly. Make sure that the curved platen load the specimen diametrically. Attach the micrometer dial gauge so that they can measure the closure of the jaws. Now you are set and ready to load. Apply the load on the specimen continuously and gently and at the recommended constant rate of 200 Newton per second. So you can fill the specimen in 1 to 5 minutes. During loading, measurements of load and displacement should be recorded. It is important to record the load when primary fracture is observed, because this load is the load at failure. If loads are recorded automatically by a data logger, you can use the peak load as the failure load. 10 specimens per sample should be tested, or based on practical considerations. From the test recorded load at a failure or peak load, we can calculate the tensile strength by the equation here. Sigma t equal to 2p divided by pi dt. In this equation, P is the load at the failure in Newton. D is the diameter of the specimen, and the T is the thickness of the specimen. Both D and the T are in millimeters. The calculated tensile strength is in megapascal. Theoretically, 2p divided by pi dt is the maximum tensile stress along the diameter across the loading points. This tensile stress is acting to split the disc along the diameter across the loading points. The maximum tensile stress is at the center of the diameter line. If the tests are done correctly, the maximum tensile stress occurs around the middle of the diameter line across the loading points. The specimen should fail by splitting along the diameter across the loading points. If failure is localized failure, not by splitting the disc along the diameter, then the test is not valid. The data from this test should not be used for strength calculation. You may read in some articles they are computing tensile deformation modulus by measuring tensile strain using strain gauges as shown here. This is wrong. The tensile stress in the specimen is not uniform. The stress is a maximum at the center and is zero at the circumference. What the strain gauge measured is the average strain over the length of the strain gauge, which is under a non-uniform tensile stress. Therefore, the measured strain is not corresponding to the measured tensile stress. Report on Brazil tensile strength tests should include the following informations. A. Rock sample information, including lithological descriptions, grain size, rock anisotropy, sample location depths, sampling date and the methods, storage history and environment. B. Specimen information such as number of specimen, method of specimen preparation, diameter and thickness, and water content observation. C. Date of testing and the test duration, number of specimens tested, machine information, and the loading procedure. D. Descriptions of failure and other observations, photographs of specimens before and after testing. E. Recorded loading at failure or the peak load. Calculated tensile strength for each specimen expressed to 3 significant figures, together with the average tensile strength for the sample. Point load test is a test specially designed and used for rock testing. The strength determined from the point load test is the point load strength. It is a simple test to perform, particularly on rock cores, without the need to prepare the specimens. In this part, we will go through how point load tests are performed. The suggested procedure to conduct the point load test is given by this ISIM suggested method made in 1985 by the International Society for Rock Mechanics and Rock Engineering. Point load tests are done by using a loading frame, a loading system with load control and measurement, the point load conical platens, and measuring devices for the distance between the platens. The photo on the right is a typical point load tester available commercially. The point load to the rock specimen is by the point load conical platen made of hardened steel. The shape and the dimension are specified by the ISIM suggested method. Point load tests were initially designed for testing on rock cores. By insert a long core between the point loading platens across the diameter. The load is along the diameter of the cores and break the core across the diameter. Continue testing along the length. We can do many point load tests on a long core and obtain many point load strengths quickly, and this is the most common way to conduct point load test. Point load test, however, can be done on almost all types of rock specimens of a variety of shapes. We can do the test on flat surfaces of cut cores, on cut blocks of cubic shapes. We can even do the point load test on uneven surfaces of natural blocks or lamps, as long as they are more than 30 millimeter thickness. The size and the shape suitable for point load tests are shown by the illustrations on the right, as suggested in the ISM suggested methods. The basic test procedure is to put the rock specimen between the two loading points of the conical platen and load the specimen to break. For tests on core specimens and the point load applied across diameter, usually referred as diametrical tests on core. We start with measuring and record the core diameter and make sure the core has sufficient length so that the loading point to the core end is at least 0.5 D. Then we insert the specimen in the point load device and close the platen in contact with the core along the diameter as in illustration. Then load is increased steadily such that the failure will occur within 10 to 60 seconds. Failure load or peak load is recorded. If we have the core cut in short cylinder or thick disc with thickness greater than 30 mm and the thickness to diameter ratio between 0.3 and 1, then point load test can be done by loading on the two flat end and across the axis. After measuring and recording the specimen thickness and diameter, then we insert the specimen in the point load device and close the platen to contact the core end in the center. The loading point on the center of the circular plane as shown by the illustration on the right. Then load is increased steadily such that failure would occur within 10 to 60 seconds. Again, record the failure load or peak load. Point load tests can be done on cut blocks or regular shapes. The thickness must be more than 30 mm. Width and length should be greater than the thickness. Specimen thickness should be measured and recorded. We can conduct point load tests at the site and on the field, and the specimen are natural blocks or lamps. Select the blocks close to rectangular cubic shape with thickness greater than 30 mm and the width and length greater than thickness. It is difficult to measure the specimen thickness. Instead, we should measure the distance between the two loading points after the specimen is inserted and held by the point load platen. This is the thickness of the specimen along the loading line. The loading procedure is the same as before. After inserting between the loading platens, apply load steadily to break the block in 10 to 60 seconds and record the failure or peak load. On the point loading, lock specimen breaks across between the two loading points. Point load strength is defined as the failure or peak load P divided by an equivalent area of breaking surface. So the dimension of the point load strength is the same as the stress, usually in megapascal for rocks. We first calculate the uncorrected point load strength, IS, as P divided by dE square. Because the point load test is originally for testing on rock cores, dE is therefore the equivalent core diameter. For a diametrical test on cores, dE of course equals to the actual core diameter d. For axial test on cores or blocks and lamps, the minimum breaking plane is rectangular. The equivalent diameter dE is 4a divided by pi, where a is the minimum cross-sectional area of the plane through the two loading points, which is the minimum width through the loading axis times the thickness between the loading points. The standard or corrected point load strength is to correct the strength to 50 mm diameter. This is the IS 50, given by IS times a size correction factor F. F is calculated as dE divided by 50 and take a power of 0.45. Standard point load strength IS50 is a standing alone strength index used in rocket mechanics and engineering. Not all the point load tests are valid. Tests with specimen breaking across the whole thickness through the loading points are considered valid, and the strengths determined are acceptable. Tests of localized failure, not through the loading points, are not valid, as those shown in D and the E on the right figures. For examples with anisotropy, loading access to wake plane angle must be specified. Anisotropy has a great impact on point load strength. When wake plane is parallel to loading axis, it gives the lowest point load strength. There should be at least 10 tests to be conducted per rock samples. Point load test report should include the following descriptions and results. A. Rock sample information, including lithology, sample type, whether core or natural block, its anisotropy, sampling location and the depths, date and method, and sample conditions. B. Specimen information and the measurements such as number of specimens, method of specimen preparation, specimen shape, specimen size, and the measurements. C. Testing information, testing data, machine, number of specimens tested, failure pattern descriptions, and the photographs of samples before and after tests. D. The results. The tabulated values of size measurements, peak load, IS, F, and IS50 for each test, and average IS50 for each sample. We are coming to the end of this session. Covered Brazil tensile tests and point load tests on rock materials. Next session, we will move to testing rock joints. Goodbye and see you at the next session.